A presentation on the iron carbon equilibrium diagrams, in which the topics to be discussed are the iron carbon equilibrium diagram, the phases of iron and carbon alloy, along with the critical points, isothermal reactions, peritectic, eutectoid, and eutectic. So, myself, M. Kiran Kumar, MTech, CL Mechanical Engineering, Government Polytechnic, Kataram. So the topics to be covered already discussed. So those are again iron carbon equilibrium diagrams with the different phases of iron and carbon alloys with critical points and the reactions, isothermal reactions, namely peritectic, eutectoid, and eutectic reactions. So let us start with the introduction. The alloy of iron carbon system include steel and cast iron. So the alloy of iron carbon equilibrium diagrams or the iron carbon system include steel and cast iron. So let us see by adding the carbon content what happens. So the alloys with carbon content up to 2% are known as steels. So the carbon content maximum up to 2% is known as steels. Alloys with carbon content above 2% are known as cast irons. So the below 2% are known as steels and above 2% of carbon content are known as cast irons. So the iron carbon system provides the most prominent example of heat treatment. So now let us move to the types of steels. Here the eutectoid steels. Coming to the eutectoid steels, in which we are having hypoeutectoid steels, hypereutectoid steels, and eutectoid steels. Let us have a look. So the steels with the carbon content from 0.008 to 0.8% are known as hypoeutectoid steels. And the steels containing carbon from 0.8 to 2% are known as hypereutectoid steels. Steel with a carbon content of 0.8% is known as eutectoid steels. So overall we can say that three types of steels: hypo, hyper, and eutectoid steels. So hypoeutectoid steels from 0.008 to 0.8%, whereas hypereutectoid steels from 0.8 to maximum 2%, and the steel with a carbon content of 0.8, exactly 0.8% is known as eutectoid steel. Eutectic steels now. So coming to the eutectic steels, iron having carbon in the range of 2 to 4.3%. The carbon content is 2 to 4.3%. Then these type of steels are known as hypoeutectic steels. In the eutectic steels also we are having hypo, hyper, and eutectic. So 2 to 4.3% can be called as hypoeutectic steels, whereas the carbon content of 4.3 to 6.67% are called as hypereutectoid steels. So from 4.3 to 6.67% are known as hypereutectoid steels, hypereutectic steels. So these are eutectic steels. So let us move to the critical temperatures. So here let us have a look over the graph. Here the critical points for 0.2% of carbon and the temperature given here in degrees centigrade. So 700, 750, 800, 850, 900. So these are the different curves formed, cooling curves, AR1, AR2. So this is a heating curve. This is a So let us have a look about the what are these curves AR1, AR2, AR3 and AC1, AC2, AC3. So let us see. The structural change due to heating or cooling causes arrest of temperature. The temperature will be arrested. So the structural changes takes place commonly at constant temperatures called as critical temperatures. So coming to the critical temperatures at which this particular structural changes takes place are known as critical temperatures. Most these are constant temperatures, and the temperature arrests at a particular point where the temperature is arrested is known as a critical point. So given as A points. So temperature arresting points of the are called as critical points. So let us see what are the critical points in iron carbon equilibrium diagrams. So these arrests occur at slightly higher temperature on heating. So the higher temperature given by AC and compared with the cooling is known as AR. So heating is given by A subscript C and cooling is given by capital A subscript R. So what is the purpose of taking C as subscript and what is the purpose of taking R as subscript? So let us see. The letter C indicates the word chafage. So which means that it is heat, to heat or heating. And whereas R is taken for the word refroidisment. Refroidisment means similar to the refrigeration or cooling. So which is means that to cool. So C means to heat and R means to cool. That's why for heating capital A subscript C and for cooling capital A subscript R can be taken. So if a piece of eutectoid steel is allowed to cool slowly, it will be observed that cooling proceeds at uniformly retard rate up to critical point, nothing but given as AR1, which is allowed to cool slowly eutectoid steel. So given by AR1, capital A R subscript 1. So the evolution of heat due to the transformation of austenite into perlite at critical point results in increase of temperature of the steel. In spite of cooling at uniform rate, it will be increasing the temperature. The steel will be observed to glow. So whenever the transformation of austenite to perlite is observed at a particular critical point, this results in increase of temperature and increasing the glow of the steel. So this phenomenon can be called as recalescence. So a reverse change takes place on heating. A reverse change is taking place on heating. So the absorption of heat due to the transformation of perlite into austenite at critical point AC1. But this is again heating. AC is given for heating, results decrease in the temperature of the steel known as decalescence. So AR1 is known as recalescence and AC1 is known as decalescence. So now let us move to the nomenclature of the change of points given by A1, capital A1, capital A subscript 2, capital A subscript 3, and capital A subscript CM. So what are these? Let us have a look. Let us identify the points in this particular iron carbon equilibrium diagram, and later let us move to the discussion. So first, let us have a look of ACM here. This is ACM we are able to observe here, ACM. And now let us start with the A1. A1 is here, A1 along this particular line, 0.025 percentage of carbon, A1 and A2 here at 723 degrees centigrade, and A3 is given here 910 degrees centigrade, nothing but 1670 Fahrenheit. So A1, A2, A3 and ACM. So the iron carbon diagram having the carbon percentages given 0, 1, 2, 3, 4, 5, 6, and here at the end we are able to see the 6.67 percentage, and here the temperature in degrees centigrade along with the Fahrenheit. So starting with the 0, 32, 392, 752, 1112, 1472, 1832, 2192 and 2552 Fahrenheit, nothing but 1400 degrees centigrade temperature, and 2912 is the maximum temperature we are able to observe. And here we are able to see the temperatures 200, 400, 6, 8000, 12, 16, 1200, 1400 and 1600 degrees centigrades. So here these are the different phases: perlite plus ferrite, perlite plus cementite, and here we are able to see the A2 again 770 degrees centigrade, even though given as 723 degrees centigrade, but 770 nothing but 1418 degrees Fahrenheit. So that is a combination of perlite plus cementite. Coming to the here, cementite plus perlite plus transformed ledaborite. So we can discuss the combinations of austenite plus cementite plus ledaborite here in this phase, and cementite plus ledaborite here. So this is the liquid phase. So let us see the different temperatures. So here let us start with the UCT, upper critical temperature point, known as A3 is the temperature where the ferrite starts to form as a result of ejection from austenite in the hypoeutectoid steels. So A3, we are able to see the A3 here, 1670 degrees, 1670 Fahrenheit, 910 degrees centigrade. So where ferrite starts to form as a result of ejection of austenite in hypoeutectoid steels or hypoeutectoid alloys. So at the upper critical temperature ACM, so here again after coming to ACM, the upper critical temperature ACM, what happens here? Below which cementite starts to form. Here at this ACM temperature, cementite starts to form as a result of ejection from austenite in the hypereutectoid steels. Previous case was hypoeutectoid steels, and here it is hypereutectoid steels or alloys. So coming to the lower critical temperature, nothing but LCT point A1, it is a temperature of the austenite to perlite, transformation of austenite to perlite. At eutectoid transformation, below this temperature, austenite does not exist. So austenite to perlite, A1. So here, this is the A1. And a magnetic transformation temperature known as A2. Here we are able to see A2 1418 Fahrenheit, nothing but 770 degrees centigrade or 723 here. So at A2 temperature, magnetic transformation occurs, and this A2 is the temperature below which alpha ferrite or alpha iron, alpha ferrite is ferromagnetic material. So if we want to clearly understand this iron carbon equilibrium diagram, we need to know these particular points. So first, let us start with the presence of various phases in different regions of a diagram. Nothing but what are the different phases? What are the different phases, and what is cementite, ferrite, perlite, austenite? So what are these combinations at different phases, at different regions in this particular diagram? We need to know. So their relative properties and various temperatures and compositions. So what is the carbon composition or carbon content at a particular phase, at a particular temperature? We need to understand at which the phase transformation takes place. Nothing but the different compositions and different temperatures and the properties of the composition at which phase transformation occurs. So we need to know that. So steel is an alloy of iron and carbon containing less than 2% carbon, as we have discussed. So if the carbon percentage is less than 2%, it can be called as steel. So steel is an alloy of iron and carbon containing less than 2% carbon. So cast iron, similarly, cast iron is an alloy of iron and carbon containing more than 2% of steel. So the more than 2% of carbon. So here this is the total diagram of iron carbon equilibrium diagram, total contents. So let us see the different phases and what are the different compositions at the different phases and the different temperatures and different critical points, different phases, different critical points. Let us have a look. So here horizontally we are having the carbon content compositions 0 to 6.67%, and vertically we are having the temperatures. So now let us look over the horizontal side where at different carbon contents, what are the, either it can be called as steel or cast iron, or it can be called with a different names. Let us have a look. So starting with 0 to 0.8% of carbon, it can be called as hypoeutectoid steels. So first is eutectoid phase and next is eutectic. So here 0 to 0.8% of carbon with iron in iron can be called as hypoeutectoid steels. So if the carbon percentage increases from 0.8 to 2, then that can be called as hypereutectoid, and that steels are known as hypereutectoid steels. So 0 to 0.8% hypoeutectoid steel and 0.8 to 2% of carbon in iron known as hypereutectoid steels. So now above 2% of carbon can be called as cast iron. We have already discussed. So this particular from 2 to 4.3% of carbon can be called as hypoeutectic steels. So hypoeutectic cast iron. So here we can't call it as steel. Why? Because it is above 2% of carbon. So from 4.3 to 6.67% of carbon, those can be called as hypereutectic cast iron. So these are the composition of carbon in the iron carbon equilibrium diagrams considering steels and cast irons. So now let us move to the different temperatures at which these particular transformations or phase transformations occur. So let us start with the temperature 0, 100, 200, 300, 400, 500, 600, 700 and 723 degrees centigrade. Next 800 and 900, then 910 degrees centigrade. Next 1000, 1100, 1200, 1300 and 1400 degrees centigrade. Next 1492 below 1500 degrees centigrade. Next 1539 degrees centigrade. So these are the temperatures. So now let us see the different points or alphabets given. What is the purpose of giving them? So here A, capital A, capital B, then C, D, A, B, C, D, E, F, G, E, F, G. Next K, L, M, N, O, P, R, P, S. So these are the different alphabetical order given. So let us see the combinations, different combinations. So here, as we know, this is a liquid or a liquid phase. So now let us just check the compositions present from 0 to zero point 0.8 steels. 0 to 0.8 steels, nothing but hypoeutectoid steel. The first phase is perlite plus ferrite. Next is from 0.8 to 2% of carbon, known as hypereutectoid steels. The combination is perlite plus cementite. And hypoeutectic cast iron, where 2 to 4.3% carbon along with perlite and the transformed ledaborite plus cementite. Next, from 4.3 to 6.67 carbon content is known as cementite plus ledaborite, so which is eutectic, hypereutectic cast iron. So here let us see the combinations of austenite here in this particular phase austenite, and here austenite plus ferrite, and this is liquid plus austenite, liquid plus cementite, and austenite, ledaborite and cementite, cementite plus ledaborite. Let us elaborate them with different temperatures in our explanation. So here we were discussing the iron carbon equilibrium diagram. So let us start with the pure iron uh, at A, that is at 1539 degrees centigrade, and melting point of cementite will be 1560. So here this is 1539 and the melting point will be above this, which is given by 1560. So ABCD is a liquidous line. See, observe here. Let us start with ABCD, given as A, B, C, and D. So A, B, C, and D. This is a liquidous line, and AHJECF is a solidus line. So here A, H, J, ECF. So this is a solidus line. So here, from here, this is a solidus line. So the region between these two lines represent liquid and solid phases. So the line HJB is the temperature transformation of delta to gamma iron. So let us have a look of H, J, and B. So here, this is J. HJB is the temperature transformation of delta to gamma iron. So here this is given as the delta iron. So this is the delta iron given here. So the temperature transformation of delta to gamma iron can be found at HJB. So this is B, this is J, and this is H. So in the alloys with less than 2% carbon, the structure upon primary crystallization is known as austenite. So that is below NJE. So N, J, and E. So this is NJE given as austenite. So which is below 2% carbon comes under steels, and here if it is below 0.8 can be called as hypoeutectoid steels, and if it is above 0.8 up to 2, then it can be called as hypereutectoid steels. So coming to the alloys more than 2% carbon, as we have discussed, the structure is ledaborite. The structure will be ledaborite plus excess austenite or cementite. Nothing but that category comes under cast iron. So the primary austenite and the austenite in the eutectic mixture contains maximum amount of carbon, that is 2% in the solution at the end of crystallization. So from 1130 degrees, 1130, carbon precipitates from austenite, and at 723 degrees centigrade, the austenite and the austenite in ledaborite containing 0.8% carbon, the perlite transformation takes place at that temperature. Nothing but 723 degrees centigrade, the transformation takes place. And below 723 degrees centigrade, ledaborite is a mixture of cementite and perlite. So below 723 degrees centigrade, ledaborite, mixture of cementite and perlite. And this particular perlite, which is a mixture of again ferrite and cementite. So now let us move to the critical points. The temperatures at which the transformation in the solid state occurs are called as critical points. So in hypoeutectoid steels, the line GS A3 represents upper critical point, UCP. GS, nothing but A3, whereas PS, A1 represents a lower critical point, A1 lower critical point, A3 upper critical point. In hypereutectoid steels, SE, ACM represents upper critical point, and A13 SK, line SK, represents a lower critical point. So here, we can clearly see the different combinations of alpha iron, beta alpha, gamma and delta irons. So here these are given in degrees centigrade, and this side it is given by the Fahrenheit. So now let us move to the solid phases where alpha ferrite. So the solid solution of carbon in iron at 0 degrees centigrade, this is pure iron. It has BCC crystal structure, body centered cubic crystal structure. The maximum solubility of carbon in iron is 0.02 percentage at 723 degrees centigrade, which is alpha ferrite. So having BCC, and the solubility of carbon in iron is 0.02 percentage at 723 degrees centigrade. So at the same 0 degrees centigrade temperature, the solubility falls to 0.008 percentage. So the carbon atoms are located in the crystal interstices. So which will be the interstitial form of, it's not a substitutional form, it is an interstitial form. So now let us move to the austenite. The solid solution of carbon in gamma iron is known as austenite. So austenite is a solid solution of carbon in gamma iron, and it has a FCC crystal structure, nothing but face-centered cubic crystal structure with a high solubility for carbon compared with alpha ferrite. So the solubility reaches a maximum of 2.08 at 14148 degrees centigrade. So the solubility decreases to 0.8 percentage at 723 degrees centigrade. The carbon atoms are dissolved interstitially. So the difference in solubility between the austenite and alpha ferrite is basis for hardening of steels, nothing but whatever the sentence says. So the difference in the solubility between austenite and alpha ferrite is the basis for hardening of steels. Hardening of steels depends upon this particular solubility factor. Next is cementite. Coming to the cementite, it is an intermetallic compound having 6.67 percentage carbon and 93.3 percentage iron. Cementite is a hard brittle compound with orthorhombical crystal structure. Each unit cell has 12 iron and 4 carbon atoms, 12 Fe and 4 C atoms. Delta iron. So this is a solid solution of carbon in iron, has a BCC crystal structure, body centered cubic crystal structure. So the maximum solubility of carbon in iron is 0.09 percentage at 1495 degrees centigrade, and this has no real practical significance in engineering. So here let us see the different forms again at different points. A, B, C, D liquidus line, H, J, E, F solidus line. Continuously let us see the points A, B, C, D, E, F, G, H, I, J, K, L, M, N. So N is here, O, P. So here let us see the perlite and the ferrite, nothing but the high hypoeutectoid steels here. So austenite and ferrite, whereas this phase is ferrite, nothing but alpha iron. So here this is austenite, gamma iron, and this portion is ferrite, nothing but the delta iron. So alpha, gamma, and delta irons. So now let us move to the isothermal reactions. So the three lines HJB, HJB, and ECF, and PSK. So here PSK. In the diagram, these three indicates the three isothermal reactions at the fixed composition and temperature. So let us see what are those. So in this particular diagram, first is peritectic reaction. The formation of austenite at 0.18 degrees centigrade, 0.18 carbon content at 1492 degrees centigrade temperature from the liquid and solid phase. Nothing but liquid plus gamma iron. So under cooling austenite and under heating again forms a liquid plus delta iron. This is a delta iron. So coming to the eutectic reactions. After peritectic, let us move to the eutectic reactions. The solidification of liquid 4.3% of carbon at constant temperature of 1130 degrees centigrade into two-phase mixture. So the liquid under cooling becomes austenite plus cementite, known as ledaborite. This ledaborite on heating again forms a liquid. So the eutectic mixture of austenite and cementite is called as ledaborite. So now let us move to the eutectoid reactions. The decomposition of austenite, 0.8% of carbon at constant temperature of 723 degrees centigrade into ferrite and cementite is known as eutectoid reaction. The decomposition of austenite to ferrite and cementite is known as eutectoid reaction. So here austenite becomes ferrite plus cementite, nothing but known as perlite. On heating again becomes austenite. So the eutectoid mixture of ferrite and cementite can be called as perlite. So the phases in iron carbon diagrams, liquid. So here this is given as phase and these are the symbols. This is the description. Liquid given by symbol L, liquid solution of iron and carbon. Delta ferrite given by delta, interstitial solid solution of carbon in delta iron, high temperature BCC phase, body centered cubic phase. Whereas here it is austenite, gamma iron, interstitial solid solution of carbon in gamma iron, which is FCC phase of iron, nothing but phase centered cubic phase of iron. So coming to the ferrite, given by alpha iron, which is a interstitial solid solution of carbon in alpha iron, which is at room temperature BCC phase, body centered cubic phase, which is soft and ductile. Next is cementite, given by the symbol V3C, intermetallic compound of iron and carbon, which is orthorhombic system, hard and brittle. So this is the structure of ferrite. And this is structure of ferrite and this is the structure of austenite. Under microscopic examination, we have took this particular figures. So invariant reactions in iron carbon system. So the horizontal line always indicates an invariant reaction in binary phase diagrams. So horizontal line. So in peritectic reactions, delta 0.1 percentage of carbon plus liquid 0.5 percentage of carbon get 1492 degrees centigrade gives 0.18 gamma percentage of carbon. So coming to the eutectic reaction, similarly from liquid 4.3 carbon 1130 degrees centigrade, gamma 2.1 carbon percentage to Fe3C 6.67 percentage of carbon. So next eutectoid reaction. Eutectoid reaction at 723 degrees centigrade. So gamma 0.8 percentage of carbon gives alpha 0.02 percentage of carbon plus Fe3C 6.67 percentage of carbon. So here let us have the eutectoid reaction. So gamma 0.8 percentage gives alpha plus Fe3C 0.8 gives 0.02 and 6.67, which is given by perlite, and this is the structure. So here in this particular diagram, we can see the compositions of weight of carbon, the temperatures 400, 500, 6, 7, 8, 9, 1000 and 1100 degrees centigrades. So here, this is the structure Fe3C formed at 723 degrees centigrade. And this is the gamma iron formed plus Fe3C. So this is the at 723 degrees centigrade. This is 700 and this is 723 degrees centigrade. Next, the same eutectoid fraction of cementite in perlite. So coming to the cementite, which can be given by this particular relation, perlite and cementite, 0.8 minus 0.02, 0.8 minus 0.02 by 6.67 minus 0.02, which is calculated as 0.117. So amount of Fe3C in perlite tie line below eutectite temperature can be calculated as 0.117. So the development of microstructure in a hypoeutectoid steels. So this is so let us see here. So this is alpha plus Fe3C. This is a perlite structure. And this is Fe3C and this is alpha eutectoid. And let us see here, this is gamma iron having alpha here, gamma plus Fe3C. So this is the structure of pro-eutectoid ferrite. You can see the dark shades and light shades. And this is dark shade is known as perlite. This white shade is known as pro-eutectoid ferrite. And this is a microstructure of a hypoeutectoid steel, 0.38 percentage of carbon. So the fraction of perlite in hypoeutectoid steels. So fraction of perlite which is given by below Te is equal to F austenite above Te. So the tie line above the eutectide temperature Te, which can be calculated as 0.8 minus 0.38 by 0.8 minus 0.2 can be total calculated as 0.54 percentage. So now let us move to the development of microstructure in hypereutectoid steels. So this is proeutectoid Fe3C, this is proeutectoid, and these are eutectoids Fe3C, and this is alpha iron, alpha, and this is the perlite structure, and here this is gamma Fe3C, and this is gamma plus Fe3C. So this is the structure of perlite, this is the perlite, and this is proeutectoid cementite on prior austenite grain boundaries. This is. So the fraction of proeutectoid cementite in hypereutectoid steels. So this is the structure given. Fraction of proeutectoid cementite, which is equal to fraction of cementite above Te, can be calculated as 1.4. So this is 1.5, this is 1.4 minus 0.8 by 6.67. This is 6.67 minus 0.8, which can be calculated as 0.10, nothing but 0.1. So phase versus microconstituents. So coming to the phase, a phase or a mixture of phases which has a distinct identity in microstructure is called as a microconstituent. And perlite is not a phase, it is microconstituent, which is a mixture of two phases, alpha and Fe3C. So here eutectoid steels alpha plus Fe3C known as perlite, hypoeutectoid steels alpha plus Fe3C perlite plus proeutectide ferrite, and hypereutectoid steels can be given as alpha plus Fe3C perlite plus proeutectide cementite. So this is the structure for eutectoid steels, and this is the structure for hypoeutectoid steels, and this is structure for hypereutectoid steels. So with this we have completed the topics, and let us have a summary of the topics covered. So initially we have started with the what is a steel and what is an cast iron, and we have studied that the iron with carbon content of up to 2% are known as steels, and above 2% of carbon in iron can be called as cast iron. So later we have discussed about different types of steels, eutectoid steels, where 0.008% to 0.8 are known as hypoeutectoid steels, and 0.8 to 2% are known as hypereutectoid steels, and exact 0.8% are known as eutectoid steels. So later discussed eutectic steels, so which range from 2.4 to 4.3% known as hypoeutectic steels, and 4.3 to 6.67 known as hypereutectic steels. So later studied about the critical temperatures and critical points given by ACAR, A1, A2, A3, ACM, A12, 13. So we have studied the different terms like recalescence, and decalescence. And as I already discussed, A1, A2, A3, ACM, these are the critical points we have discussed as a part of critical temperatures at which the phase transformation occurs.